Assalamu alaikum. Hope you're doing fine. We have got the expression for electric flux for a flat surface placed in uniform electric field. In this video, we are going to get the expression for electric flux for a curved surface placed in non-uniform electric field. For that, I consider this as the non-uniform electric field. Now, I have told you earlier, an electric field in which electric field lines are not parallel is referred as non-uniform electric field. Here, the arrow mark represents the direction of electric field, E vector. In one such non-uniform electric field, we take a curved surface, which is not flat. Okay, I have taken one curved surface. Now I'll show you how to get the expression for electric flux for this kind of curved surface. Now suppose I consider A as the area of this curved surface. A is the area of this curved surface. Then, in order to get the expression for electric flux, I divide this curved surface into large number of segments, each having area delta A. I take it as I divide this a large number of segments. I take the area of first segment as delta A1 vector. Area of second segment is taken as delta A2 vector. For third one, A3 vector. It goes this way. I take n number of segments. The area of nth segment is delta AN vector. Now, how this area will appear? Let me show you. I take one area element. Appear something like this. Then, we know area is a scalar quantity. Then why do we have this vector symbol here? Here, if I draw a line which is perpendicular to this surface, this perpendicular line is known as normal. This normal represents the direction of the area element. I name this area element as AI, delta AI vector. This is the direction of this arrow line represents the direction of area element delta AI. And the electric field line which is passing through this one. Repeat, here I consider this area element as a flat surface, and electric field passing through this one is considered as uniform electric field. Now, for this case, it is taken as EI vector. Now, in simple words, I will explain this to you with the help of a simple example of what we have done here. Say, suppose I have a curved surface. This is not a flat one. In this kind of a curved surface, if I take a small area, if I divide this into large number of small segments, then what happened? I take one such small segment here, very small segment. See, if I take this small segment, you can find this one. Just okay. Now, if you look at this small segment, you will find it appears to be straight. See, straight. It is not curved here. Though the segment is a curved, the entire line, if you take, it is a curved line. But the segment that I have taken appears to be flat. So the same concept is applied here. We have divided this entire arbitrarily shaped surface into small segments. When we have done so, each segment appears to be in the form of flat surface. Okay. Then the electric field which is passing through each segment is considered as or almost uniform. So the electric field which is passing through this area is E1 vector, and through this area element is E2 vector, and the electric field passing through this area element is E3 vector, and so on. Here the electric field passing through this area element is E3 vector. Now all these electric field passing through these segments are considered as or almost uniform. So if you multiply these two, we will get the electric flux. So we know the expression for electric flux. 5E is nothing but sorry, it is not E3, it is En for nth segment. Let me change this. Now, what I was saying, when we multiply area with the electric field, we get the electric flux. So, E when multiplied with the area, we get the electric flux. So, by keeping this in mind, I am going to get the electric flux for each segment. Then I am going to combine them together to get approximate electric flux for this curved surface. Let me do that. Take it as 5E is equal to the product of electric field through area element A1 plus electric field through area element delta A2. Now multiplying these two, we get the electric flux to this area element, and we will do the same for all the area elements, and at the end we get this last one, nth segment En into delta An vector. Now here electric field is a vector point, so we have used a arrow mark in everything, arrow ahead. So I go ahead. Now we know very well in mathematics as well in physics, whenever we come across a summation, we use a symbol. That symbol is nothing but sigma. Here sigma stands for summation. So I generalize this. I take the place of 1, 2, 3, I take I. Okay, EI vector dot delta AI vector. Here I stands I is equal to 1 to n. Okay, this is the final expression for electric flux. Now, suppose the limit of a delta AI, limit of delta AI, limit of a delta AI vector tends to 0, then the above expression will be written something like this. Here we write phi e as such. In the place of a summation, we will write integration. Then E vector, I don't write I. Then delta. In the place of delta, I will write D, which stands for differentiation. D A vector. This is the expression for electric flux. Electric flux. I box this. Now, what does it say? Now, from this we understand that the electric flux for a given surface depends on both the electric field pattern on the surface area and the orientation of the surface with respect to the electric field. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your questions in the comment section. Thanks for watching.